One of the most common forms of data analysis when you collect data is that you plot that data and you fit it to a curve, and the parameters of that curve tell you something about the physical phenomenon of the situation. For example, maybe you measure something falling, you fit that data to a curve, and you can extract the gravitational constant, for example. The easiest way, of course, to do this in Python is using the curve fit function. I have a video on the curve fit function on my channel, so if you haven't seen that, be sure to check that out. Today, we're going to look at something a little more particular. You'll notice that most of the curve fit functions in most computational libraries return both the optimal parameters of the fit, but also corresponding errors on the parameters. And it's these errors which are so prone to misinterpretation. In this video, I'm going to attempt to show you exactly what those errors mean, and we'll do it through practical coding examples. This whole video, by the way, is based on one of the questions in an assignment on my new Udemy course. This course covers everything I think you need to become a successful programmer in STEM, whether you're doing scientific analysis or engineering applications or some sort of mathematical work as well. There's a link to the course below as well as a discount code, so be sure to check that out. So the only packages we'll really need to import today are NumPy, Matplotlib, the curve fit function, and we're going to look particularly at the chi-squared function. The chi-squared probability density function, and that's exactly what it is very related to the process of curve fitting data. So let's go over what happens when you curve fit data. You fit to a curve y equals f of x beta. Okay, we'll discuss what this means, but you collect some x data and y data, and you can plot that on a 2D plot, for example. And the idea is that you want to find a function, f of x, that depends on some parameters beta, such that when you draw y equals f of x beta, it sort of goes through the data points here. The data also have errors, which I'm going to call sigma data. And the idea of the curve fit function is you define your function f, maybe f is equal to beta times x squared. So beta is just one parameter. Then so you have an idea of what this function f looks like. Then what you do is you find your optimal parameters beta using a curve fit function, such that the so-called chi-squared value is minimized. So the chi-squared value is defined like this. And you'll note, like I said earlier, chi-squared is actually a PDF, a probability density function. But usually it's defined, chi-squared is defined as follows. Chi-squared is equal, okay, you sum over all data points. You take the difference between your function evaluated at that data point with your parameters beta, you subtract the y value of that data point, and you divide by the errors. And of course, you square each of these. And if I plug this all in together, once I do my curve fit, I get the so-called chi-squared value. So I think it's useful. Let's actually make some data and go over some practical examples here. So here I'm just defining some x data. It goes from 0 to 2 pi. Some error data. Here I'm using the NumPy random normal function. So of course, I can call this function. And if I plug in 2, for example, it will give me, I need to import my libraries. It will give me two variables that are Gaussian random variables with a mean of 0 and a standard deviation of 1. So that's exactly what's happening here. Of course, if I want to sort of adjust the mean, I can add plus 0.1, or if I could add 5, and then the mean of this Gaussian is now 5. If I want to change sigma, I can multiply this by 0.1 to get sigma equals 0.1. So what I'm saying here is that my errors on my y data are, okay, they have a sigma value of 0.1, and I'm going to create, well, 20 of them because I have 20 x data points here. So I have my x data and the errors on my y data that are just Gaussian errors, and my y data is going to be just 3 times the exponential minus 2 times x. So it's 3e to the negative 2x, plus, of course, the errors that I have on my y data. So I can generate this x data, y data, the corresponding errors, and I can plot the data. So I plot my x data, y data, the error on the data, and these are some parameters I personally like to give when I'm creating a error plot. I like the error bars in this format. So you can see here I have my y, x, and these are the sort of data points and the corresponding errors on each data point. So I've sort of randomly generated the errors. Some of them have more errors, some of them have less error, and it sort of goes like this. All right, so we've randomly generated these data points with the corresponding error, and what we want to do is we're going to fit it to an exponential decay function, y equals a e to the negative bx. So the parameters beta, if you think of beta like a vector of all the parameters, beta is equal to a comma b. So this is the function that we're going to fit to. And so I define my fit function here, x a b, that should be a e to the negative b times x. Of course, you would expect in an optimal fit, a would be approximately equal to 3 because that's how we defined it here, and b should be approximately equal to 2. So here I define my fit function. Again, this is what I do in the curve fit video. You can check that out. Again, there's a link below to curve fit. And I can call this function on my fit function. This is what I want to fit the data to, my x data and y data, as well as the errors on the y data to get my optimal parameters, p optimal parameters, and my covariance matrix. And as you know, you can extract the errors on your parameters as the square root of the diagonal entries of the covariance matrix. Okay, I'll show you what that means in a sec. So here I call my curve fit on my data, and as you can see, I have my optimal parameters here, p optimal. So yeah, it's about a is equal to 3 and b is equal to 2, sort of what we expect. My covariance matrix looks like this, right? So this is my covariance matrix. If I want the corresponding error on the parameters, I take the square root of this element. That gives me the error on a, since a was the first parameter in the fit function. And the error on, or the square root of this gives me the error on b. So that's why I take the diagonal elements, np.diagonal of the covariance matrix. And then, of course, I can call square root, and that gives me the errors on the parameters. And I get the following values here. So obviously getting the errors on the parameters isn't too difficult, but the hard part is interpreting what these means, and that's the whole point of this video. Of course, then we can plot the actual function result, y equals a to the negative bx, with the optimal parameters next to the data. So that's when I get my x model. Of course, this is representative of the function, so I go between the minimum of my x data, maximum 100 points, so there's a lot of points for the plot, and the y value corresponding to the model, I just call fit function with the x data I create, as well as the optimal parameters. Of course, star here, because optimal parameters is an array of 2 values in this case. The star will just feed in this as the next argument, and then this as the next argument. So it's a way of separating arguments in a function call. So I got my x model and y model, then I plot the model next to the data. This is the same plot that I made before. And you can see I have my data next to my best fit model. And of course, these are my optimal parameters, and this is my error. So the question is, what do these errors mean with respect to these optimal parameters? So the question then is, what do these errors actually mean? It's interpreting them that's difficult. But before we get to that, we should digress a little bit to really understand what is a chi-squared value, right? And for that, we need to understand the chi-squared distribution. And I have this square here, but chi-squared is like a single variable. It's like x or w or something. Chi-squared, it's just a single variable. And it's essentially a probability density function. And the probability density function depends on a parameter, the degrees of freedom. So the degrees of freedom is equal to n. So really, if I write this, I should say the probability density function, it's a function of chi-squared, but it depends on n because n gives you a different probability density function. It's a family of probability density functions. Each child in that family is a different degree of freedom. So this is how it's defined here. It's 1 over this. This is just a constant. It's a number times e to the negative chi-squared over 2. Well, chi-squared is the variable, so it's an exponentially decaying function, times chi-squared, and then n over 2 minus 1. So it's essentially just a basic probability density function. So for example, if I create some x data in the range of 0 to 40, I can call the chi-squared.pdf function. So chi-squared, by the way, I've imported this. It's a SciPy stats continuous distribution. If I call .pdf, this is actually a function. And if I plug in x and the degrees of freedom, in this case, it basically evaluates this function, the probability density function, at each of these x values that I feed into it. So I can create some x and y values, and we'll actually plot what the distribution looks like. So here's chi-squared for a value of 18 degrees of freedom. Of course, I can change this to, well, let's go 3 degrees of freedom, right? And I plot this, and you can see that it's very sort of close to the origin. And as the degrees of freedom gets larger, the probability density function, of course, shifts to the right. Now, the main thing is that it's always normalized. All probability density functions are normalized so that the area under this curve is equal to 1. So no matter what value I give for the degrees of freedom, whether it's 2 or what it is, it's always, if I take the integral of this function from 0 to infinity, that's where chi-squared probability density function is defined, the area under the curve is always equal to 1. So we'll put it back to 18 degrees of freedom, and this is what our probability density function looks like. And there's a reason why I chose 18, and we have 20 data points, and so we'll get to that. So the question is, what exactly is this probability density function? What does the degrees of freedom mean? Of course, why does it have the name degrees of freedom? Why not just call it n? Well, let's talk about that. So The chi-squared distribution is derived from other probability distributions. And the simplest probability density function is the normal function, the bell curve, right? A normalized bell curve gives a really nice probability density function. So this is where you understand the chi-squared distribution. The chi-squared distribution, this distribution you see here, is the probability density function of the following sum. So it's the sum over I, ni squared. So the question is, what the heck is this? Well, ni of mu sigma is a Gaussian random variable with mean mu and sigma. So ni it's a random variable that's distributed according to a probability density function with a standard deviation of 1 and a mean of 0. So it's a bell curve centered at the origin with a standard deviation of 1. Now, if I take a bunch of those random variables, so I take one, another, I keep drawing random variables from this distribution, I square them and I sum them all together, that's going to give me the chi-squared distribution. That is the chi-squared distribution. So I sum these all together, I get a number, and if I do this over and over, so I sum it all together, I get one number. Then I draw a bunch of these again, I get another number, and I get these chi-squared numbers. And if I plot the distribution of those numbers, they'll follow this distribution here. So, okay, that might be complicated. Let's actually do it here. So here might be how I generate a single chi-squared random variable. Well, I know that the np.random.randn, right? If I just call it 1, it will give me one random variable like this. Now, what I want is I want to square a bunch of them together. So let's square 10 of them together, right? So here's 10 numbers. Let's square all of them. So now I have each of these random variables. They're independent from each other and they're squared. And of course, I can sum them. So here I call np.sum on this, and I'll get the sum of all these variables. And that gives me a chi-squared number with 10 degrees of freedom. And I can keep calling this over and over, and it will keep generating different chi-squared random numbers. And I claim that the distribution of these numbers, well, in this case, I would have to give 18 because this has 18 degrees of freedom. If I give 18 here, I claim that these numbers, if I create a bunch of them and plot a histogram of them, they'll follow this distribution here of the chi-squared distribution. So let's actually do that. Let's generate a bunch of these and make a histogram of them. So I'll set the degrees of freedom to 18. So you might be confused what I'm doing here. This is a really cool operation, by the way, so I'll go into exactly what's done. So here I'm creating degrees of freedom times 10,000. So if I go like this is going to give me a lot of numbers, right? Let's do it below here. Degrees of freedom not defined, so let's define 18 degrees of freedom. So this is going to give me, I don't know, 180,000 variables here. Now I can reshape this array, which is sort of what I'm doing. Well, let's square it first. So we'll square it. So now I have a bunch of ni10s squared, a bunch of them. So I'll go like this. I have a bunch of them squared. Now what I'm going to do is this array here has length 180,000. So I can reshape it. Let's do that here. So I'll add a bracket to this side. Bracket to this side, and I'm going to reshape it so that the shape is 10,000, which of course is this number here. This is, by the way, is how many chi-squared variables I'm going to generate, and it's going to be 10,000 by 18, right? So now I have an array that I have, well, if I look at the shape of it, for example, there's 10,000 rows by 18 columns. So I have 18 of these per row. So if I sum all the elements of each row together, I'm going to get a chi-squared variable with 18 degrees of freedom. And I have 10,000 rows. So I sum all the elements in each row together, and I do that for all 10,000 rows, and I'm going to get 10,000 chi-squared variables. So that's what I do here. I sum across the first axis. Of course, that's the axis where I sum across each row. And then as a result, I get an array of 10,000. I can check the shape of this. 10,000 chi-squared numbers. So again, if you don't understand that, go through it slow. It's just a quick way to generate 10,000 of these values here. Of course, the other way to do that is just to use a for loop, generate this number many, many times, append to a list. But this is the more functional way to do it in Python or NumPy, for example. So anyways, now I have 10,000 chi-squared values. If I run this cell, it's going to give me chi-squared values. I can look at it, and the shape is going to be 10,000. So now what I can do is I can plot all 10,000 of these numbers on a histogram and compare it to this distribution here, which has 18 degrees of freedom. So let's actually do that. So for that, I plot xy. I'm going to plot the probability density function here. Then I'm going to make a histogram of values over top of this. Now the way to do that is to make a histogram of the chi-squared values that I have in this array, 100 bins, and I'm going to use a density plot. And what the density plot is, it ensures that the sum of all the bins of the histogram equal 1. And now, because a histogram, of course, gives you numbers. Like these are small numbers here. Now, if I take the integral of this curve, I get an area of 1. If I plot a histogram of bins, by using density, I get an area of 1. So let's actually start by looking at that without the density equals true on. This will actually give me a histogram where each of these is the number of counts. So I get 300 values, of course, like about between, say, 11 and 11.1 is what it's telling me. Now, if I use density equals true on this histogram, it's going to normalize it so the sum of all these is equal to 1. But then it becomes the same shape as the probability density function here. Anyways, as you can see, the chi-squared distribution in blue corresponds to this experiment where we generated a bunch of normal random variables here. We summed them together, we squared them, we manually obtained chi-squared values, and of course that follows the distribution we want. So we've looked a lot at chi-squared distributions. The question is, how is the chi-squared distribution and all these parameters related to the curve fit parameters? Well, let's look at some similarities between what we did here with this sum and this sum here, which shows up when we minimize the curve fit function here. Now you'll note that I have capital M1 here and capital M2 here. I left those different on purpose. But you can imagine we're sort of doing a similar thing in each of these sums. Here I'm taking a bunch of random variables that are distributed according to a normal distribution with a mean of 0 and a standard deviation of 1. And I claim that that's the same as this sum here. Well, how could this be the same as this sum here? Well, I want you to think about each yi. Remember, that's a data point that we measure in the real world. And in the real world, data is going to be noisy. And if you think of each data point as a Gaussian random variable with mean value equal to the model function, so the model function actually does describe reality, is what we're saying. If I evaluate this model function at the x data point value with the true parameters, this is like the true physical phenomenon parameters. In the case of like gravity, for example, g is minus 9.81. But when you measure that in an experiment, you'll get something close to that, but not exactly that. Anyways, beta true is the true parameters. So yi is the Gaussian random variable with mean value equal to this here. And standard deviation, the error that you're going to measure on that data point, is equal to sigma I. So that's the error on your parameters. Well, then what I'm doing here is it's like when I take this value minus yi, it's like I'm taking a Gaussian random variable that has a non-zero mean, and I'm shifting it so that it does have a zero mean here. And when I divide by sigma I, that Gaussian distribution is wide. By dividing it, I shrink it, or I expand it, depending on the value of sigma, and so that the standard deviation now becomes 1. So this term here normalizes the mean of the distribution, and this normalizes the standard deviation. So these two sums look very similar. Now you might be wondering, well, why the heck are capital M1 and capital M2 different from one another? Because surely, of course, this is like you're summing a bunch of random normal variables together, and this is a bunch of random normal variables together. So they should be equal when M1 and M2 are equal. Well, for that, we really have to be careful here. In the first sum, I have a bunch of random variables that are all independent of one another. And I claim in this case, these random variables are no longer independent from one another. In other words, each term in this sum depends on all the other terms of the sum. The reason for that is that the optimal parameters of beta are obtained using the curve fit function. And the curve fit function takes in all the x data and all the y data. So I use all the x data and all the y data to get beta optimal, and then I evaluate this sum. But the problem is that because beta optimal depends on all the data that I measure, the terms in this sum are no longer independent of one another. Now, if instead of beta optimal, that's obtained using the curve fit, I somehow knew what beta true was, so I put beta true in here, beta true is not obtained using any data. So in that case, these two sums would be equal for M1 equals M2. But because I'm using beta optimal, which is obtained using the curve fit function on data that we actually measure, these aren't going to be equal. Now, there's a beautiful mathematical theorem, and I'm not going to attempt to prove it here because it's very complicated, and it's a very convenient result. And it tells us, well, okay, maybe the terms here are dependent on one another. Maybe they are independent here. Well, it turns out that if capital M1 is slightly smaller than M2, it's equal to M2 minus the number of parameters in beta, then these two sums are distributed according to the same probability distribution. And that's really nice because we know that this sum is a chi-squared distribution with capital M1 degrees of freedom. And so that means we also know that this sum here is also a chi-square distribution with m1 degrees of freedom, where m1 is equal to m2 minus the number of parameters in beta. So it's equal to the number of data points minus the number of free parameters. That's where you hear about the degrees of freedom being number of data points minus free parameters. That's where this comes from. And the mathematical theorem you need to prove to show that is very complicated. So I've wrote a function here. All it does is it evaluates this sum. I plug in my x data, my y data, my optimal parameters, my model function, and the error on my parameters. And I basically evaluate the model function from x data, the optimal parameters, subtract the y data, square it, divide by the sigma squared, and this basically will give me the chi-squared value for this particular data set and the particular fit function that I have. So I can run this, and let's actually compute the chi-squared value for our old fit. So I have my x data, my y data, the errors on my y data, the fit function, and the optimal parameters that I basically got up here early in the video. And I compute the value of chi-squared, and it's equal to about 19.23289. And you'll note that I had 20 data points. If I look at this plot here, there's 20 data points and there's 2 free parameters in my fit. There's A and B. So I get a chi-squared value of about 19.239. And so we think, okay, well, is that a reasonable chi-squared value? Well, if I look at this distribution here, 19 is well in the range of this probability density function. It's a reasonable number to get. So that's the value of chi-squared we get for that particular realization of the data and the curve fit that goes along with it. So I said that this chi-squared value is for that particular set of data. Now the idea is that if I measure a new set of data, I'll get a new chi-squared value, and another new set of data, I'll get another new chi-squared value. And if I do that over and over and keep measuring data sets and keep getting chi-squared values, and I sort of make a histogram of those, I claim they'll be equal to the chi-squared distribution with 18 degrees of freedom, which is this blue curve here. Sort of like how I drew these values here from this experiment. Now I'm going to draw data. I'm going to do a curve fit function. I'm going to do all of that, get a chi-squared value, and do that many, many, many times. And I'm going to make a histogram of the values. So that's exactly what this function does here. Here I'm creating some x data, that's the data that you measure in the field, some y error data that gets added to the y data, so that this is sort of like the mean of the Gaussian distribution of the data that I'm measuring. The y error data, it's sort of adding Gaussian noise to it. The Gaussian noise has a sigma equal to 0.1. So the error on each one of my y values is 0.1. That's the true standard deviation. So that's important for below, because here I'm calling the curve fit function on my fit function that I'm optimizing for. X data and y data, data that I'm fitting to get the function. And my sigma, well, my sigma is equal to 0.1 for every data point. That's the 0.1 here that gets added here, each of the y data, right? It's a Gaussian random variable where sigma is equal to 0.1. So sometimes it will be close to 3 times e to the negative 2x. Sometimes it will be a little bit greater if there's a greater error. But the point is that the standard deviation on each one of these errors is equal to 0.1. Then I call the get chi-squared fit value, x data, y data. It's going to be 0.1. It's an array of 20 0.1s. That's exactly what this does here. If I call 0.1 times np.1's 20, it will just give me 20 0.1. So that's like the error on each y value here. So I create this function. It curve fits. It gives me the chi-squared value. And I can evaluate a bunch of different chi-squareds and plot. So here I'm getting 10,000 different experiments. Remember what I'm doing here. I'm creating a new data set. I'm curve fitting it and getting a chi-squared value. So doing this 10,000 times is like running 10,000 experiments where I collect a new data set every time. Then I can plot these chi-squared values next to my model function here, like I did above, only this time I'm doing it with creating new data sets. And I get the following distribution here next to the chi-squared values. So sure enough, if I run this experiment many times, computing a chi-squared value each time, I get chi-squared values that are distributed according to the chi-squared distribution. Rather, a better way to phrase that is I get values of this sum here, and I've shown that if I compute this sum here for many different collections of data sets, this sum is distributed according to a chi-squared distribution. So often we call this the chi-squared value. The reason why we call it the chi-squared value is because we know it's distributed according to a chi-squared distribution. So again, we haven't talked about the error on the parameters, but everything we're doing up to this point is to build to that discussion. So we've shown that this sum here is distributed according to a chi-squared distribution with m minus beta naught degrees of freedom. So beta naught is the number of free parameters. I take the number of data points, subtract the number of free parameters, in my curve fit function, and that's the chi-squared distribution, which this sum is distributed according to. So, by the way, we've shown that this is only true, it's only distributed according to a chi-squared distribution for the optimal value of beta. So we have to take our data, do a curve fit to get the optimal value of beta. Then when I evaluate the sum, it's distributed according to a chi-squared distribution. It is not distributed according to a chi-squared distribution for some other value of beta. It's only distributed according to that distribution above here when I make this histogram when beta is the optimal value of beta. It's the optimal parameters. So I think this is what confuses a lot of people about chi-squared minimization, right? You say, oh, you're minimizing for chi-squared value. And they look at this chi-squared probability density function and they think somehow that, okay, well, we're going to get to the smallest value on this curve. That is the incorrect way to understand it. The correct way to understand it is that each experiment gets you a different value of chi-squared. And this function is only distributed according to a chi-squared distribution with the optimal parameters of beta. So you're not adjusting beta and moving downwards on this curve. No, your chi-squared value is already set. And when you minimize to get the optimal parameters, you're just finding your place on this curve for that particular experiment. And if you do another experiment, well, your chi-squared value is already going to be set. You optimize for beta, you minimize this term, and all you're doing is you're finding where you lie on this curve here. So the main point that I have bolded here is we only get a true chi-squared value. In other words, we only get a variable that's distributed according to the chi-squared distribution when the sum is actually minimized. Okay, so now we can define the error on the parameters. We have all the tools and functionality to understand what it means. The errors are defined as follows. If delta A is an error on A optimal, so I have my optimal parameters and my error on my parameters, I showed them above. If delta A is an error on A optimal, then delta A is defined as follows. And you have to be very careful here. If I insert my optimal parameter plus or minus the error, so my optimal parameter is 2, and it tells me my error is 0.1, then suppose I insert 2.1 into beta. So A, so 2 optimal plus the error is 0.1. So now I'm inserting A is equal to 2.1 inside beta. And then I re-optimize all the other parameters except for A to get a new set of optimal parameters. Then this will make the following sum here increase exactly by 1. And by the way, this should be a beta optimal prime. So I get a new set of optimal parameters such that I fix the value of A to be the optimal value plus delta A. I sort of re-optimize to get beta optimal. I re-evaluate the sum. And it turns out that this sum will increase by exactly 1. So here I'm going to define my fit function with one parameter. Remember, I have to fix the value of A as the optimal value plus the error. So here I'm going to say, okay, well, my new parameter, remember, now I'm only going to fit for B. The second parameter in A e to the negative bx, I'm fixing the value of A. We're only going to fit for B. And so my function now only takes in x and b, and it returns the fit function, which is A e to the negative bx, but I'm fixing the value of A to be the optimal value of A plus the error of A. So I'm going A optimal plus delta A. And it takes in x, it takes in this value, and it takes in b. So this new function only takes in x and b and returns this value. So we've essentially created a function f of x equals A optimal plus delta A e to the negative bx, where this is a fixed constant, sort of like how e is a fixed constant. This is a fixed constant that you're multiplying out front, and we're going to sort of optimize for b. So to do that, of course, now we're making a new set of optimal parameters. Of course, this is the case where I'm only optimizing for one parameter. So it's only going to give me one optimal parameter here because I'm only fitting for b. So it will give me my optimal value of b and the corresponding error for b. So I use the curve fit function using this function here with my x data and my y data and my corresponding error. Then I can compute the chi-squared value for this data here. So it's the data set that I collected before with the error and the sort of fit function parameter. In this case, if I sort of evaluate this, well, I'm going to get a chi-squared value. But let's look at what fit function, well, let's look at p optimal one parameter. This gives me my optimal value for b when A is sort of set like this. And my covariance with one parameter, well, it's no longer a matrix, it's just one value. This gives me the error, of course. Well, it gives me the, if I take the square root of this, I get the error on b for this fit. But don't worry about what that means. This is the optimal parameter for b if A is sort of fixed like this. And I compute my chi-squared value, I get 20.27. And you'll note that the chi-squared value for my old fit, where I was optimizing for both A and B, is 19.23. So I've gone up by approximately 1. Remember that curve fit only approximates the errors. But sure enough, the chi-squared value here is about 1 less than what it is here. So the main conclusion of this video, what do the errors mean in the curve fit function? Well, the error delta A of an optimal parameter A optimal is defined such that if you fix the parameter A is equal to A optimal plus delta A in your set of parameters, and you re-optimize for all the other parameters, then the following sum here will increase exactly by 1. Now, in the case where this is beta optimal, like the true optimal parameters, this is distributed according to a chi-squared distribution. The reason why I don't call it makes the chi-squared value increase by 1 is because in this case, where you change the value of A and re-optimize for the other parameters, this is no longer a chi-squared distribution, but it does make the sum increase by exactly 1. So that ends the video. Congratulations if you made it to the end. I hope you now understand what the error of curve fit parameters means. If you made it to the end, I would highly suggest checking out my Udemy course. I have many examples like this to really understand what the interpretation of a lot of things that you do in scientific analysis is. A lot of the times you might curve fit or you might do something else and you don't really understand what actually is going on behind the scenes, what the errors actually mean. So check out that course, be sure to like and subscribe, and I'll see you next time.